Um, First of all, I'd like to say a few words about our speakers. The first speaker is Toby Harris. He is currently Director of the Space Applications at HEO, supporting the development of novel space-based imaging capability. Before joining HEO, he worked at Astroscale as Global Head of Space Situational Awareness, responsible for ensuring SSA needs for their current and future missions, and before becoming Director of Government Relations and Space Policy. Previously to this, he was Head of Orbital Systems within the Chief Engineer's Office at the UK Space Agency, where he oversaw technical aspects of licensing UK spacecraft and helped develop the UK licensing process and UK space flight policies, which are in place now, and supported the creation of the 2018 Space Industry Bill. He also he's headed the UK delegation to UN COPUOS Scientific and Technical Subcommittee and represented the UK as policy lead for the Interagency Debris Coordination Committee. And he is currently chair of the UK Space Domain Awareness Group. Our second speaker is Hannah Dorr. Hannah Dorr as a Space Mission Intelligence Analyst at HEO, focusing on the applications of non-Earth imagery, NEI. She studied her bachelor's degree in aerospace engineering at Swansea University and her master's in space exploration systems at Leicester University. Hannah is also the previous executive trustee of the Students of the Exploration and Development of Space, UK SENSE. I think now is the time to hand over to the speakers. I will go and sit down there. Thank you very much for coming, and have a good talk.
Great, thanks Howard. I've just realised on the title I've said is instead of are, so apologies for that. My first mistake so far. Anyway, thank you very much. So my name's Toby Harris, and I'm going to talk a little bit about what HEO do and what non-Earth imagery is. We're going to do a bit of a double lap between myself and Hannah, and then look forward to your questions later. So first of all, can you just raise your hands if you've ever heard of HEO before? Brilliant. I'm glad to see Jack's heard of it. He's a fellow employee at HEO UK. And has anyone here heard of non-Earth imagery before? A few there. Brilliant. Okay, excellent. That's good to hear. So just a quick overview of the presentation today. I'm going to talk a little bit about who we are, what we do, how NEI works, or non-Earth imagery works, a bit about non-Earth imagery in action, so we'll show some of the pictures that we've taken using these techniques, and then I'm going to hand over to Hannah, who's going to talk about some of the applications of non-Earth imagery, sort of the why case, why are we bothering to do this at all, and also about our platform, HEO Inspect, and then I'll talk a little bit about some of the software and hardware developments we made and a few bits and pieces at the end. So first of all, who are we? So we're actually a spin-out from Australia's University of New South Wales. So we're an Australian company. We're based in Sydney, or at least our headquarters are in Sydney. Set up in 2019. We now have a London office as of a few years ago, which is based just outside MOD main building, not too far from here. And we've recently opened our Washington, DC office just late last year. So there's only 3 of us in the UK. There's 25 or so in Australia, and there's just two in the US. We recently closed a Series A funding round of about $8 million to expand and grow across all 3 regions, which we were very happy about, and that happened late last year. And our mission is to effectively, rather ambitious, image anything in the solar system on demand. So that's obviously our mission. We're just going to start with things in low Earth orbit because it's probably the easiest, and perhaps the moon as well. But the longer term goal is to be able to actually image anything. And actually this company, the original idea was to focus on near-Earth objects, so NEOs, asteroids, that kind of thing, with the objective of trying to image it, providing additional information should we ever want to mine an asteroid. Turns out that's quite difficult, both imaging it and mining it. So again, we're sticking with some things a bit close to home for the moment and see how that goes. So non-Earth imagery, what is non-Earth imagery? Also referred to as satellite-to-satellite imaging, or SAT-squared, or space-to-space imaging, involving the use of space-based sensors to capture resolved imagery of resident space objects. So it's using sensors onboard satellite platforms in orbit around the Earth, taking resolved images, so it's not just dots in the background, it's actually images where you can actually resolve and see features of an object, of resident space objects, so anything pretty much in orbit around the Earth. So how does non-Earth imagery work? So NEI is a type of inspection. So inspection is where you basically get very close to an object and you can understand exactly what it is, what it does, what its capabilities are, that kind of thing. And you need resolved imagery to do inspection. Now, in space, inspection is quite hard. Traditionally, you do inspection by taking a spacecraft with a camera and wandering up close to another spacecraft, perhaps a few hundred meters away, and taking images. Now, what we do with non-Earth imagery is we exploit the use of close approaches or conjunctions. So everything that's going around the Earth, eventually they come reasonably close, certainly in low Earth orbit, they come close to another object. Pretty much everything comes close to another object after a while. And what we do is we take advantage of those conjunctions. Now, in the world of space situational awareness, satellite operators are worried about coming close to another object, so they don't want to get hit by it. So often these SST operators, they typically would try and determine when conjunctions happen to warn spacecraft operators that they might collide with something and they need to move out of the way. We welcome these conjunctions because we're coming closer to another object so we can take a picture of it. And so what we do is we use satellites with cameras that are already up there, and there happens to be quite a few Earth observation satellites already in space, and we borrow them. And so that way we can actually use the existing satellites that are up there when they're sort of going over the sea or something like that, when they're not being used. We borrow them for a small period of time, and we point them at things that we're interested in taking pictures of. And it means that we don't use any propellant, we don't use any fuel, anything like that. We don't have to build satellites, we don't have to commission spacecraft or anything that might cost a lot of money. We can effectively use the spacecraft that are already up there, and it becomes more of a software problem than anything else. And Earth observation satellites are perfect for this. So how does HEO perform non-Earth imaging? So at the bottom left there, we have this online portal called HEO Inspect that Hannah will show you a bit later in the talk. Effectively, what you do is you type in your satellite that you're interested in imaging, and then it would go to the next stage. It would determine all the potential close approaches that satellite, that object that you're interested in would have with our imaging satellites. And it would very quickly whiz through all of those and determine when the next opportunity might be. It will then take that information and it will send it straight up to one of the satellites that we have access to, no humans in the loop, and it will immediately task that satellite to take an image when it comes into that sort of close encounter region. That would take a certain amount of time. It really depends on the orbital mechanics and how far apart the satellites are initially. Once they get close enough, get to that opportunity, normally between 24 and 72 hours, it takes that image, so it slew the satellite around, take an image, put the satellite back the way it is, and then send that image to the ground. That would normally take about sort of an hour to 2 hours, something like that. That really depends on how quickly the satellite can download its data. And then it will go to our space mission analysts at HEO, people like Hannah and Jack. And then they'll analyze the data, they'll extract information about the image, and then they'll send it back to our platform for our customers or ourselves to look at the imagery and use it in whichever way we see fit. So what is our current coverage? So we use existing Earth observation satellites. These are a couple of our suppliers at the moment, Axel Space and Satellogic, and they are about 450 to 500 kilometers in altitude above the Earth. And that means that most of the coverage that we have and most of the good imagery that we can take happens in that kind of region. And you can kind of see that sort of color coding there in terms of altitude versus the best possible resolution. Once you get above 700, 800 kilometers, it gets quite a long way away from these satellites, and so we can't really use them anymore. So at the moment, we can cover most of LEO, about 2/3 of low Earth orbit, and in the future, and I'll talk about this a bit later, we plan to expand to high LEO, high low Earth orbit, so above 800 kilometers in altitude, and then ultimately to GEO as well, which is much, much higher, about 30,000 kilometers in altitude. So what are our capabilities? Imaging. Obviously, we're using Earth observation satellites to take pictures. This is one of the things that we focus as one of our capabilities. We have about 35 Earth observation satellites we have access to at the moment to perform this tasked imaging. They can use visible, panchromatic, or multispectral sensing. So they've got a variety of wavelengths they can use to take images of these other objects. And we can do either what's called static flyby imaging. So that is where you basically keep the satellite pointing in one direction and wait for that target spacecraft to fly through to take an image, or you can do slewed, which is where you start moving the satellite with the thing you're trying to image at the same time. And that has the advantage of reducing motion blur. You can imagine when you're taking pictures of spacecraft in low Earth orbit, things are traveling very, very fast, about 10 kilometers per second relative velocity. So by doing that, you reduce the motion blur and you can get a clearer image. You can also keep the object in the field of view for longer, and so you can actually see perhaps how it's rotating, but I'll talk about that in a second. Insights and analysis. So once you've got your images, that's great, but what do you do with them? So we can actually extract a lot of information about the objects themselves, their size, shape, geometry, etc., from these images, and we've worked very hard to try and work out how we can extract as much information from these images as possible. We're also doing a lot of 3D modeling. It's a great way of trying to provide data or information about the images we take by recreating them into 3D models and then using the information to improve the 3D models or create new 3D models. Simulation as well, talk about this a little bit later, but we're building our own simulators to try and recreate the imaging that we do, and I'll show you why that is. And then hardware. We're currently also building our own cameras to try and expand our constellation of sensors. So, non-Earth imagery in action. I'm just going to go through a couple of examples of how we've used non-Earth imagery, and then I'll hand over to Hannah to talk about some of the applications. So, the International Space Station, our favorite thing to image. The reason being it's nice and big, it's easy to characterize, and it's a great object to try and take images of. So these are a couple of images that we've taken recently of the ISS. You can see that some of them are taken with clouds in the background, so the sensor's pointing down towards the Earth as it takes the image, and then you've got other ones where it's pointing up towards the sky, and that's why it's sort of a darker background, so so-called dark space imaging. And most of these images are taken at sort of about 30 centimeters per pixel, which is fine for the ISS, because it's a big old space station. And like I said, we have a variety of frequencies of taking these images at. So that one on the left there is in near infrared. We also have green, blue, etc. And this is a 3D model we developed as well to try and represent the images that we see. So the ISS is perhaps not that interesting, but it's a great application for other objects that we might want to image in the future as well. The Chinese space station, Tiangong. So this is one of the spacecraft or space stations that we've been imaging since they started building it back in sort of 2020, 2021. And what we did is we took images at a regular frequency, and from that built a 3D model to try and reconstruct how the space station was actually built in the first place. And so we kind of matched the 3D models that we had with the images that we took on a sort of regular basis every few months. And that way sort of explained and almost looked at the pattern of life of how you build a space station like this. Now, typically, if you're just using ground-based telescopes, ground-based sensors, you're not going to get much more than sort of a dot of light or tracking where the modules are in relation to each other. But here we can actually see how the space station itself was actually constructed. Now, what I really need is some sort of epic music or something like that. Otherwise, I feel like I have to talk through the whole video. So I understand the station features about 3 permanent pressurized modules now, and it might be more than that actually, typically with 3 people on board all the time. And so there's a sort of a red, green, blue color image of the space station at the end there. So what about some harder things? Rocket bodies and upper stages. When rockets reach orbit, they deposit the topmost part as a rocket body or upper stage. They're very easy to identify by their cylindrical shape, and they're also quite large as well. So on the left there's an SL4 rocket body. In the middle, there is an H2A upper stage, which is actually done in a stacked multispectral image, so we've got some color there. And then on the right, this is an unknown object. We weren't sure what it was. We took an image of it, and then it was clearly a cylindrical shaped object that's quite similar to a CZ-8 rocket body. Satellites. They obviously make up most of the population of active and intact derelict objects in space, and our sensors are able to capture unique images of some of these spacecraft. So on the left there is our Landsat 4 satellite, imaged quite a high resolution with a low motion blur that enabled us to get quite a crisp image. And you can see sort of the 3D modeling that we used to recreate the attitude of that spacecraft at a given point in time. We also imaged Landsat 5, the Kuiper P2 satellite, which I believe is the first image of its kind of one of the Kuiper satellites, and then METOP A as well. And again, you can kind of compare the 3D model that we constructed to the image to try and understand things like the attitude. Okay, I'm going to hand over to Hannah to take us on a journey of some of the applications that you can do with non-Earth imaging.
Thank you. So now I'm going to kind of explain the main features that we can gather as insights from NEI, and then kind of the case studies for what we can use for this. So first we have object identification. So when satellites are launched into orbit, sometimes you don't know which order that they are released into space, or if there's any debris that is unexpected, or sometimes they may be active payloads from other countries that you don't know what they are. And so we can take a photo and be able to identify these features. So object 1, 3, and 4 here are previously unknown objects that we've managed to identify as active payloads. And we can also see the configuration and kind of the size of those satellites as well. Object 2, instead of being an active payload, is actually a second stage rocket. So people who are tracking and trying to understand what is in space may not be as interested in continuing to track that object as accurately as the others, since the others are in fact active payloads. For measurements, we can also try and understand the configuration and what these satellites and objects look like. So in terms of what we expect to be in space, we can validate if this is in fact what is actually in space or not. And this can also help with some other applications such as active debris removal and re-entry, which I'll move on to now. But in terms of the images on the slides, we have the Landsat 4 again, which we saw previously, and also our ERS-2 image that we took for an active re-entry campaign for UK Space Agency. For the active debris removal, a lot of designs in terms of the satellite that has to go up to collect these debris objects, the design is kind of informed with what they expect to go and collect, and a lot of the time ground-based observations can't actually tell you the state of the object that you're going to collect. So where we can actually see what's going on in space, this can be a cost-effective way to sort of de-risk ADR missions, as you can understand if solar panels are deployed, if other substructures are deployed, and kind of if those are intact, rotating, freely movable, or kind of fixed, which can greatly save on costs like fuel costs, because then you can narrow the solution base that you need to do in terms of when you go to actually create your connection with that piece of debris. And where you can understand the configuration, you can also understand the attitude and its orientation in space. And from that, you can also derive the tumble rate assessment, which can be useful in a number of applications, such as the ADR and re-entry, as you'll want to know its dynamical effects as it goes throughout space. This can also help operators understand what's going on with their satellites. If they have lost contact, we can try and understand if they're in safe mode, if it's tumbling, and when those ground passes might be, so that they can get back in contact with their satellites. For license supervision as well, we have been able to actively image 2 different spacecraft in the same imaging campaign, as you can see through the images here. You have the ISS and Crew 5 as an example of seeing a close approach of 2 different space objects. This can be used to try and ensure compliance with the Space Industry Act and other political kind of things that you need to comply with when it comes to space. We also did the re-entry campaign for UK Space Agency to help with our activities in terms of tracking and understanding re-entry. I've forgotten the word, but re-entry of satellites. So here we have the graph that shows when the images were taken for ERS-2. Because it is a rapidly deorbiting object, it was quite hard to get perfect pictures to understand the configuration, but you can see pictures 3, 8, 9, and 11 are high enough resolution that you can understand where the configuration of that satellite is, and therefore the attitude. The rest of the pictures we managed to confirm that it was still there. However, they are at lower resolution due to this unstable orbit that it was in, made it harder to predict the probability of success of higher resolution detail. In terms of the insights that we gathered from this campaign, we managed to get those 4 images where we could extract the attitude estimation. I've provided some examples for the pictures here. You can see the actual image that we took alongside the 3D model example of that attitude in space. ESA, whilst it was trying to predict the impact window of this satellite that re-entered last month, found it really difficult to accurately determine to a low uncertainty where this was going to re-enter, because they didn't know which kind of direction that the satellite was facing as it was re-entering. So I provided their uncertainty graph in the corner here, along with the red lines that shows where we've been able to actually obtain that attitude data. So we're hoping to investigate how these attitude estimates can affect and help re-entry prediction as initial estimates into the software for predictive re-entry. In terms of verification of object geometry, we managed to determine that the satellite was in fact still intact till an altitude of 300 kilometers, where we got our last image of ERS-2. So we can monitor for fragmentation, and we're going to try and see how low we can image for another re-entry campaign within the next couple of years. I'll just quickly take you through HEO Inspect, our platform, where all of these operations are kind of centralized. It's also where our customers can access our data. So this is some screen grabs of what the software looks like inside. We can determine if any space object is in coverage with our sensors. We can see the specific conjunctions that we have, along with the parameters that that has in terms of expected image resolution and the probability of success. Therefore, we can determine which conjunctions we would like to task. That automatically sends it to the satellite providers that we have. We get the data back on this software, and then people such as myself and Jack can go through that data to find the satellite or objects in the database to then create these insights and provide it back to the customers through our reports. I'll now pass back over to Toby to talk through the software and hardware for our company. Thank you.
Thanks, Hannah. I should also point out that everyone can get an account on HEO Inspect. There's a detail at the end of this on how you can do that. You'll only have access to the International Space Station and all the images associated with that. But if you fancy a play, then you're more than welcome to have a look at it and sign up for an account. So, HEO Simulator. So images are fine, but actually we need to do simulation of those images as well in order to make sense of a lot of them. What we find is things like attitude, for example. In order to work out the attitude of a spacecraft from an image, we effectively need to recreate that image using a simulator. And so what we do is we build 3D models, and then we process those 3D models using a simulator of the camera, and then from that we can compare the simulated image to the actual real image to extract information like the attitude of that spacecraft. And actually we're trying to do this using my current favorite buzzword, using machine learning and deep learning. So obviously we can do this manually, but it takes time and there's errors, etc. So what we're trying to do is actually train deep learning algorithms in order to do this for us, to find the most likely attitude for a given spacecraft using the simulator. So this is an ongoing bit of work at the moment. We're also looking at simulating what we think our cameras can see of specific objects. Now, it's not cheap to image a spacecraft from space. It costs money to do it because you're basically borrowing someone's satellite for a period of time. So if we can give an idea of what those images are going to be like for a known object at a known distance, then we can actually present whether it's valuable or not, whether they're going to get additional insights. And if it is, we can then do the image, and then they can actually find information that we actually need. So that's another reason why we're doing this simulation work. The benefit for HEO in developing a simulator is that we have a huge amount of validation data now. We have thousands and thousands of images taken from satellite cameras that are very well characterized. We know the orbits, we know the orientations, we know the details of the sensor, and so we're able to actually build a simulator that can hopefully very accurately replicate those images. In terms of hardware, So we're currently building our own non-Earth imagery dedicated cameras. Now, they're not too dissimilar to a typical Earth observation camera. What they are is they're buildable in a reasonable amount of time. Now, what we find when we are looking at off-the-shelf cameras for space-based utilization is it takes a long, long time to get hold of them. So we thought, actually, maybe we can build our own and we'll do a little bit better. So that's what we're trying to do at the moment. We're building our own dedicated cameras. Holmes on the left and Adler on the right. Holmes, I believe, is about 10 centimeters and Adler is 20 centimeters. And the goal of those is to plant them on as hosted payloads on spacecraft that are going to different orbits. And on this slide here, you can see a couple of the missions that have recently launched. So we currently have 2 Holmes payloads in orbit at the moment. One was launched on Turian Droid satellite on a SpaceX Transporter 8, middle of last year. And more recently than that, we have Holmes 2, which is on a Space Machine satellite launched only just earlier this month on SpaceX Transporter 10. And so currently they're still undergoing testing. So the one on the left is still going testing on the imaging system, and the one on the right, the spacecraft itself is still under LEOPS, so still doing low Earth orbit operations, etc. And hopefully we'll be able to use both of those spacecraft to improve our coverage, improve the frequency of which we can image things, and also enable us to understand how best to integrate these cameras and develop these hosted payloads in the future. So looking in the long term, what we want to try and do is increase our sensor coverage and also increase the variation of sensor types. So like I said before, we have 30 or so sensors in low Earth orbit. The more sensors we have in low Earth orbit, the more frequently we can image things. So at the moment, we can image things sort of within 24, 72 hours, which is fairly quick given how long it can take to image things if you just have one satellite, for example, wandering around LEO. But what we want to do is try and reduce that as much as possible, and also increase the chances or increase the opportunities where we get high resolution images as well. And to do that, you need more sensors in orbit, you need more satellites. As well as improving the number of spacecraft we have in LEO, or the number of sensors we have in LEO, we also want to look at different orbital regimes. So high LEO, anything above 800 kilometers. Earth observation cameras generally aren't there because they're quite a long way from the Earth, so there's not really a reason to put them up there. So what we want to do is put some of our payload cameras on some of these higher orbiting spacecraft, so we then have access to imagery at those higher altitudes. Likewise in VLEO, less than 300 kilometers, there aren't many satellites that have cameras set up. There's a few, but not very many. So we'd like to explore that as well, particularly if we're looking at trying to image objects in lower altitudes, those that, for example, that are re-entering. And then finally in GEO, there's no commercial satellites with cameras in GEO at all. So what we would like to do is start implementing cameras in GEO and begin that kind of that novel application of imagery in geosynchronous orbit. Looking on the right, we want to look at different sensor types as well. For the most part, it's all optical. It's red, green, blue, panchromatic, near infrared occasionally. So it's basically multispectral, but it's pretty much just visible. What we'd like to do is explore new types of sensor modalities. So as well as optical, we want to look at long-wave infrared, so that's thermal. If you can do thermal imaging in space, then you don't have to worry about the sun illuminating the object that you're trying to image. You can actually wait for it to go in eclipse and carry on imaging even though it's behind the Earth. And that opens up a huge variety of new options. You wouldn't believe how much the sun plays a part in looking at imaging opportunities. So if you can remove that dependency, suddenly you have a huge number of options available to you in terms of imaging. Hyperspectral, so like I said, we only image in sort of 4 or 5 wavelengths. Hyperspectral is hundreds of wavelengths, and that then lends itself to doing things like in-depth materials analysis and some interesting things involving all those different frequencies that you might be able to pick up. We're also looking at using SAR, so synthetic aperture radar. This is all mainly sort of optical visible spectrum type of spectral wavelengths. SAR using RF, it's active as well, so you're sending out radiation as well as just collecting it. The good thing with SAR is that it relies on the object moving or the sensor moving, which is perfect in low Earth orbit because everything's moving really quickly. So you don't get motion blur, it actually works for you in order to create an image. The difficulty, of course, with SAR is you need great big radar transceivers in orbit, which can be expensive. But it's one of the things that we're talking to people at the moment whether we can do. Now, HEO relies on partnerships as well as customers to bring in the money, but we also we very much rely on partnerships. We couldn't do the work we do without having a huge number of companies supporting through by being suppliers of satellites, also the software suppliers as well, etc. And we have a whole host of current customers across the globe, both in the UK, in Australia, and the US. Quite varied customer base, and we're hoping to expand that over time as the company grows in all those regions. So just in summary then, HEO performs non-Earth imagery using Earth observation satellites to effectively collect space situational awareness data or inspection data. Our platform, HEO Inspect, which is kind of like the core of what we do, enables us to do this end-to-end tasking, imagery, and analysis using these supplier satellites. The capability has broad applications to civil, defence, and commercial use, and we're hoping the capability is going to grow as our partnerships expand, as we get new sensors and we build new software. And on that note, I will end with one of our images of the moon, which we randomly took using one of our satellites, sort of a testing of whether our approach would work in the first place. And we got the moon. It's a fairly sizable target, but we're quite happy we did it. If we missed that, then we'll be in trouble. And if you do fancy having a go with Inspect and looking at some more images of the International Space Station, feel free to sign up using that link below. And on that, I will end and offer any questions.
Does this work? Yes. Well, thank you very much, Toby, Hannah. Very, very interesting discussion. My first question is, do you have sufficient clients to keep the business running today? People are asking you to expand and go further than you're doing today and investing in your company?
Yeah, absolutely. I think so at the moment, yeah. And I think it's only going to get better as we improve the number of sensors we have and improve the fidelity of the sensors as well as the software as well. I think this is one of those businesses where, because we don't have to build satellites, we can keep the costs down. And there's a wealth of applications there as well. So as these sensors get better, it's only going to go in one direction. So.
Very good. Okay. So questions from the floor. Down here, first one.
Hi. Two questions. Firstly, following the previous one, how frequently are you taking an image for a customer?
How frequently are we taking an image for a customer?
Yeah.
I mean, we take multiple images every day. Hannah, I'm not sure how many images we currently take per day. I don't know if you can.
It's around 50 per day. Some of those are successes depending on how accurate the location data is, but at the moment we're about that. Not all of those are for customers. We do take images for research and development to kind of get that data set of space objects and to train our machine learning tools. But it's around that for both of them.
And secondly, on that note of machine learning, how much of the current end-to-end process is manual, and ultimately, how much of the process do you think can be automated?
So I think, I mean, Hannah, you can say how much is manual at the moment, couldn't you?
So we can set it up to...
Hannah, excuse me. Could you stand up here, because I'm not sure that we can all hear. Yes, thank you.
So at the moment, if there's an object of interest, we can manually set it up so then it will automatically look for specific opportunities to do with parameters that we want. So we could do ideal image resolution and some like ideal motion blur. So that part in terms of actually tasking the satellite and getting the data back, that's all automated. And then once that data comes back, it goes through our AI. So then if it sees the object, it will show us where, in what frame, where it is, what it thinks it is, etc. And then the only manual process in that is the space mission analyst will double check that that prediction is correct, and then there are cases where sometimes there aren't any predictions, because if we are pointing at the Earth, sometimes like a house or a boat or some other things might confuse the AI slightly, so we will manually check those and find the results in that. But all of our data that comes back, we can turn over even with humans in the loop within 24 hours, because you've got myself and Jack doing the space mission analysis in the UK. We've also got Carla in Australia who works when we're asleep, so we have round-the-clock coverage.
Thanks.
Thank you for the talk. I'm wondering, with synthetic aperture radar, what sort of resolution you're expecting to achieve?
That very much depends on the frequency of the SAR that happens to be on orbit. So from recollection, I think there's a fair number of X-band satellites up there that could do SAR, and you could probably get resolutions probably of 20, 30 centimeters, something like that. It does depend a lot on the type of sensor itself, though. Ideally, you'd have a higher resolution than that, but I think it just depends on, you know, how these satellite operators who are using SAR perhaps want to, you know, deploy their sensors in the future.
Thank you very much for the talk. I'm an optical systems engineer at SSTL, so I'm particularly interested in the kind of imager side of things. With your partners, Axel Space and Satellogic, I think they're area array sensors. Are there any plans to expand into push broom imaging, which can be higher resolution?
Yes, we would like to go into push broom. I think it's one of the things that's on our technical roadmap. It's just a more complex approach to imaging, which is why we've stuck with sort of the snapshot imaging for the time being. But once we have a bit more bandwidth with our technical teams, then that'll be one of the things we'll be looking at, because we know there's a lot of satellites up there that do use push brooms.
Okay, and one more question, if I may. How far typically can you off-point as well with your partner spacecraft? Are you limited to kind of 45 degrees, or can you spin all the way around and try and image at higher altitudes, basically?
Well, we can point in any direction we want. Traditionally, we were just looking at the ground, so satellites would pass underneath. And that often gives you some good contrast in order to take images. We have expanded into what we call dark space imaging, where we're looking away from the Earth. But yeah, we're still experimenting with that at the moment, what we think's best.
Okay, thank you very much.
Thank you both. Are there currently any regulations around what you can and can't image, how you can share that, and will that change as your images become higher resolution?
Yeah, so in the US, the NOAA had quite strict regulations on any US licensed spacecraft taking images of other spacecraft. In the UK and Australia, there isn't any real written down regulations to that effect, but they obviously follow sort of the US's stance on that. Actually, since HEO has been about and we've been doing this imaging, they've relaxed their regulations, partly so that obviously their own US companies can do this should they choose to. So there are certain limited regulations, but I think it's only ever going to get more relaxed as the capabilities become more capable effectively, certainly from a commercial point of view.
Hi, thanks for the talk. I wanted to ask about dedicated SSA satellites. So mostly you talked about EO satellites where you're looking to turn the satellite and measure what you want. But you're probably aware there's a company called North Star Earth and Space, and they've just launched 4 satellites, I think it is, and they're one of maybe the first dedicated space-based situational awareness observation capability. It seems that would slot very nicely into your business model. I just wonder if you're aware of them and if you're talking to them about using their observation capability for your needs.
Yeah, I mean, we certainly talk to quite a few different sort of space domain awareness, space situational awareness companies. One of the key aspects that I perhaps didn't mention before is that we require very good, accurate data about where objects are in space. When you're trying to image an object flying past at 10 kilometers per second with a field of view that's sort of less than 1 degree, you have to be really precise on where you're pointing your telescope. And for that, we need really accurate information, orbital information about the objects that we're imaging, and also the sensor spacecraft ourselves. Now, a company like NorthStar that can provide that data would be fantastically helpful in working that way. So we are talking to different SSA companies and also government agencies as well on what SSA data we can get to improve our ability to image those fast-moving objects.
Thanks.
I was just wondering, kind of picking up on the lady's question, you're a commercial company. Are there any customers that you wouldn't take, or is there any kind of internal guideline you have on satellites that you wouldn't image? I mean, for example, I'm Russia, I come and ask you to image a US spy satellite. What do you say to me? I've got the money.
I think the problem with that is that we probably not do much business with the US again. So we have to be careful about what we do. Non-Earth imagery is a new and evolving area. We may sort of be the first commercially. We probably won't be the last. I'm sure this is going to be an evolving thing. But you're right. We have to be careful about who we sell to and why we're selling it to, whether it's defence, civil, commercial, etc. So we are having those kind of internal conversations, as well as talking with our regional governments as well about how we should approach this from a commercial point of view. So, yeah.
And if I was wanting to put up a spy satellite that I didn't want you to image, would I be best to go for a small CubeSat?
The smaller the better, I think. Yeah. Paint it black and make it small.
Thanks.
You briefly mentioned the sun and the sun's role in imaging. What kind of light conditions do you like to get the best images of satellites?
Hannah, do you want to take that?
So because a lot of our imagery is optical based, we kind of need the light to reflect off the satellite to be able to see the different substructures. So we do typically try and task missions for like a sun phase angle that allows the reflection to occur. But we do also have cases where it's on the opposite side. So for the ERS-2 imagery, for example, the re-entering satellite, it was a lot of kind of a black shape instead of any visible variation within that actual satellite because the sun was behind it, kind of showing the actual satellite as a shadow instead of kind of more like the ISS where you could see the individual structures on that. So it does play a role, but also with our expansion into the other sensor type modalities, some of those aren't actually reliant on the sun at all. So we will be able to image more, but also because we have such a large access to a number of satellites for the actual NEI, we don't typically have to wait long before the sunlight role that we want it to play is available.
Hello. I just wanted to know what are the challenges you have when you actually taking the pictures and using the simulator. For example, there may be some meteoroids or some unidentified objects. How do your simulator then discard those things? And the other question is regarding the use of it. For example, you're talking about commercial use of those images. I'm still struggling to understand, other than the defense of the and some agency which are sending satellite, what are the other examples of or use of those imagery which you're creating?
So are you asking what are the other use cases for this imagery?
Yeah.
I mean, we obviously, I've spoken mainly about the civil and commercial use cases as well. Obviously, there's defense use cases for this kind of imagery too, which I haven't shown too much here. And you can perhaps imagine how that information might be used. But for the most part, from a civil point of view, we want to try and provide information that effectively would help sustainability use of space. And that's why we focus on re-entry and ADR as two of the main areas that we want to try and push on, really. From a commercial point of view, we've been in discussion with various spacecraft operators to talk about how we can use it to assess faults, for example. If a spacecraft has lost contact, but it still has power, and it's tumbling, for example, can use information from non-Earth imagery to understand how it's tumbling, what it's doing, and when you might actually be able to gain contact with it again when those antennas or transceivers go over a ground station, for example. So there's those kind of applications as well from a commercial point of view that we're trying to look at as well. I don't know if that really answers your question, but...
Another question I was asking is the challenges you have with some of the objects which are there already, like some junk of the previous things orbiting around. How do you differentiate and then discard those?
I mean, the objects that we image, often we're using information. For example, I don't know if you're familiar with SpaceTrack, which is a US open source website maintained by the US government. We use information from there to identify the objects for the most part before we image them. So we know roughly what we're trying to take images of. We're not just sort of, imaging random things and hoping for the best. So we use third-party information to help make those decisions and to reduce that kind of uncertainty of what we're imaging.
Hi there, Tim Robinson, Aerospace, I come with the building. A couple of quick questions. First off, you said it doesn't use any propellant, so there's no sort of like micro thrusters to move the sort of satellites into position. There's no gas or anything being used up.
Well, the satellites. Sorry, go on.
So, yeah.
So the satellites do have propulsion. I mean, they're station kept, but for our purposes, we don't need their propulsion for anything. We use all we're doing is changing the attitude, so it's mainly reaction wheels, that kind of thing.
Okay, yeah. And the second question was, so the idea of compliance support and regulation support. So that's am I right in thinking that's traffic cameras in space to prevent tailgating?
Could well be.
Rather than speed cameras.
Yeah, potentially. It could be some sort of application like that. I mean, in the UK, certainly, the CAA, for example, they're responsible for supervising their licensed spacecraft. And currently, a lot of that is done using ground-based sensors, so tracking where they are in space. But in the world where you're going to have satellites coming close to one another and performing these complicated rendezvous and proximity operations, active debris removal, in-orbit servicing, constructing space-based solar power, that kind of thing. Ground-based sensors would just tell you that those two dots have become one dot. And so what we're hoping to provide is a way to actually say, this is what's happening, this is what's agreed upon as part of your license conditions, and this kind of verifies what they're doing.
Would insurers be also interested in that as to whose fault the collision was?
Potentially, yeah. There's always that. But I mean, we speak to insurers every now and then, and that's definitely something that could well be the case. Yeah.
Hi, Toby. This one's for you. At the start of your presentation, you mentioned that your ultimate goal is to be able to image anything within the solar system. So disregarding specifics or any future technology, how do you envision that working?
That's a great question. I think it's just a case of having more satellites with more sensors in more orbits, really. I think imaging everything in the solar system, I mean, if we're talking out to Neptune and Uranus, then there's going to be some challenges there, I think. But I think the focus at the moment is going to be LEO, GEO, and cislunar as well. There's a lot of activity going on in moving things in sort of the lunar orbit regime, and I think that's where potentially we would look at hosted payloads in those kind of orbits as well. And we'll take it step by step. I'm not sure the roadmap has quite gone to the gas giants yet, but we'll see.
You mentioned SpaceTrack, so I assume two-line element sets come into play. I'm wondering, are you using those raw to get state vectors for objects, or do you require additional state estimation for your tasking?
Yeah, so we use that data for two reasons. One is to predict all the opportunities that we might get when we're looking at particular objects. So say we want to image the ISS, we use the TLEs to work out when the next opportunities might be for us to do that, given our satellite constellation. And TLEs are normally pretty good for that. They don't need to be super accurate. They just need to give us an idea of when it's going to get within a certain distance. We then use TLEs and ideally the more high fidelity ephemeris data to do the actual imaging part. So when we upload those last bit of instructions to the satellite to say, right, you now need to point at this and take a however long second exposure at this specific time, you want as accurate data as possible in order to make sure that's kind of firmly within the field of view. TLEs do work, and we've been using them for a while. But if the TLE is out of date, then it becomes uncertain. So the more accurate, more timely data we have, the better.
Hi, I'm just curious to know some of the differences between, as you see it, maybe is using a dedicated mission, a dedicated payload intended for non-Earth imaging versus a hosted payload that's intended for Earth observation, and whether there's any key advantages, I suppose, that you see in terms of putting up your own payloads.
Now, I'm not a hardware person, so I might struggle to answer this, and then I'll hand over to Hannah and let her struggle to answer it. No, you won't really. I think, so there are some aspects towards to Earth observation systems that don't always work out great for non-Earth imagery. Now, typically for an Earth observation camera, you're always going to be 400 to 500 kilometers away, roughly speaking, from what you're imaging. And so you have things like the hyperfocal plane. So if you come within a certain distance, say like 100 kilometers of these cameras, it starts to get blurry. Now, in the case of what we're doing, we actually want to try and image things within that kind of hyperfocal distance. So with current EO systems, there's a risk that you might get a blurry image depending on how the optics are set up and how the image is set up. So that's one of the things that we try and take account of, that we are imaging things much closer than an EO camera as well. So we just need to make sure the optics reflect that. I don't know if you've got anything you want to say on that, Hannah.
I'm not a hardware person. That's what I will say.
Okay.
Given the high relative speeds in orbit, what are the minimum and maximum exposure times for your images so far?
Ooh. That's a tricky question. Maybe Jack knows, actually. Do you know that, Jack?
It varies a lot. I think at the moment we look at 170 milliseconds-ish on average.
Yeah, it does vary a bit. I mean, the longer the exposure time, obviously the brighter the image you're going to get, but then you introduce motion blur, whilst vice versa, you reduce exposure time. It might fade into the background, the signal to noise might not be high enough. So it is a bit of a balance, a bit of trial and error sometimes. It's something we're working on trying to characterize better at the moment. The more images we do, the better we get at it. So.
And also, how often would you consider a silhouette image useful?
A silhouette image?
Yeah. Well, you mentioned previously the sun being behind the object.
With ERS2, well, in the case of ERS2, even though it was a silhouette, you could still see the SAR, the central bus, and the solar panel that we all needed for attitude estimation. And the sun, for what we task, is never completely behind the satellite, so we did have a little bit of reflection on the side. So when we put that into our simulator, we have the sun in the direction that it's meant to do, where we can match up specifically with the slight reflection on the edges that you would see from just behind. So those were fine because we managed to get all of the information that we needed from it, and it can also just generically show you the configuration, so you'll know if it's a satellite because it will probably have a central bus and a solar panel or two, or it will be the shape of a rocket body or a cylinder, and then from there we know if we want to task some more missions to increase our understanding or not.
Thanks.
Hello, I'm curious about the geo opportunities, where obviously you have quite significant challenges. If you mentioned putting a camera onto maybe a geo satellite, geo satellites do tend to stay relatively in the same position to each other within their own station keeping boxes. They also tend to be mostly nadir pointing for operational purposes. What do you think about the ways in which you can actually get more opportunities for observation at that altitude?
Yeah, it's a great point. I mean, geo is difficult because it's really big. On the plus side, things are generally moving relative to one another quite slowly. They're all kind of moving in the same sort of direction.
Absolutely.
So what we've been looking at is potential satellites in subsynchronous and supersynchronous orbits, so moving just above and just below, and doing imaging that way. Doing low thrust maneuvers to move from a sort of a sub-synchronous geo orbit towards an object that we want to image, sort of very low thrust, and then back again. And then also looking at putting the cameras on spare spacecraft. So some operators are now thinking about putting additional satellites up there, either to bring into use for spectrum needs, or to actually just sit there as a spare should their primary spacecraft no longer function for whatever reason. So we're looking at all these different options about how we can do a cost-effective way of getting cameras into GEO. But it is a challenging problem.
Excellent, thank you.
I'm interested in your tasking model for customers, because I think I recall you said fundamentally the customer can task into your application and then simply get the imagery back. But obviously you also made the point that you are borrowing a sensor from somebody else who might have a specific task at certain times. How do you provide that as an opportunity to the customer? Do you do it on the basis of they can task anything they like, provide a window to the customer so they know when that imagery is going to be taken?
It's a good question, and it's something we're trying to work through at the moment. Typically, the suppliers generally have priority because it's their satellites, and if they want to image something on the ground at that particular time, then that may rescind a particular image opportunity we'll be looking at. We try and make sure that the opportunities are filtered so that that doesn't happen, particularly, for example, if the satellite's over the sea. Generally speaking, they're not being used very often, and so that makes it a higher priority opportunity. So there's a whole bunch of filters that we use at the moment to try and ensure that we capture it when we can, and that potential customers are aware that they can't necessarily do particular opportunities because of that.
Thanks.
I was just wondering, do you have to take out insurance to protect you in case something goes wrong when you're using somebody else's satellite? So either you just mentioned a small bit of propulsion, what if that put it in the path of some unknown debris, or if you accidentally pointed it at the sun and fried their cameras, would you then have to replace their Earth observation satellite, or are you insured?
That's a good question. We've never taken over the command and control to actually change the spacecraft's trajectory or anything like that. So that would be an interesting question. Maybe we do, maybe we don't, I don't know. It's not something that we've discussed yet. In terms of dazzling a sensor and killing it, certainly that was. I think it was a question of doing this crawl, walk, run type thing. So we tried very carefully initially with the suppliers, watching our every move and making sure that we were doing things in a sensible fashion. And I think you kind of build up confidence after a while. In terms of actually having insurance, I'm not entirely sure about that. I'd have to ask the powers that be. So.
Obviously, the image itself is very quick, but there's a whole process either side of that. So what's the window that you actually need to borrow someone else's satellite for?
Honestly, we use it for a matter of minutes, less than that really. Like with most satellite tasking, you can upload the commands on the pass just before the imaging, and then the images can be downloaded the very next pass. So it's very quick. The main time is actually the time in between when you want to task it and when the opportunity actually occurs. There you're kind of subject to sort of the orbital mechanics and where the sun is and all that kind of stuff. So.
Thank you. Are there any particular security concerns about using other people's satellites to image potentially sensitive assets?
We try and make sure that our system is as secure as possible to make sure that other people can't access it, for example. But what we do is, as a commercial company, everything is unclassified. We don't have any classified aspects to what we're doing. So Not really. We just make sure our systems are secure, and then we offer what we do as a commercial product.
All right, thank you.
So, as you improve your coverage from geostationary and beyond, do you see the usage of your own hardware more often than onboard imaging systems? Because onboard systems usually are optimized to look at something, whereas you're looking at something else.
I don't know at the moment. I mean, we're obviously we're designing our sensors specifically for non-Earth imaging. That's kind of what we, from the ground up. Whilst obviously a lot of the sensors in space at the moment, they're designed for other means, and we're just using them for non-Earth imagery. So in theory, our sensors that we're building should be optimized for what we're trying to do. And it kind of really depends on how quickly we can build the things compared to an off-the-shelf solution, and how much it costs as well. If it's much cheaper to build it ourselves, then we'll do it ourselves. But if another company comes along and builds lots of cameras really, really cheaply, then maybe that'd be a better option for us. It really does depend a bit.
Thanks.
Hi there. Would there be any application of having video, full motion video coming from satellites, imaging of the satellites?
It could be in the future, definitely. I think full motion video, you have issues with data bandwidth and that kind of thing. And it's never going to be in real time either, because you've still got to download the video at some point. I don't see necessarily that being a problem in the future. I think it could be something if it's valuable. And in a way, some of the imagery we have taken are basically lots and lots of frames of a single object. So they do sort of become a crude full motion video. So.
Well, I think our questions have run out. Thank you very much indeed for this very interesting talk this evening to both of you. It's fascinating that you've chosen to use a sustainable fashion to address active debris removal and looking at other applications. So it's very, very interesting. And I hope your company continues to survive and become very famous. Thank you very much indeed.
Brilliant. Thanks a lot.
So, ladies and gentlemen, I have just one more thing to say. Thank you for attending. Thank you for being here, and thank you for your very interesting questions. Very, very good. I would like to remind you of the upcoming conference on the 17th to the 19th of April. It's 3 days here. And it's called Energy from Space. You mentioned this, I think, in your discussion. It's about generating power in space to transmit to the Earth in a sustainable fashion. And so you will find this on our website. You can register right away, and we'll be very happy to see all of you at the conference. Thank you very much. Thank you for coming. And once again, we'll thank our two speakers. Thank you.